Physicists use waves to model sound and light. A wave has four important pieces. First is the amplitude. A wave's amplitude tells you how high each peak reaches above the midpoint. Second is the frequency. A wave's frequency is the number of peaks that pass by a particular point in each second. Third is the wavelength. Wavelength tells you the distance between two peaks in a wave. And lastly is the wave's phase. This tells you how far to the left or right the wave is shifted along the horizontal direction. All four of these pieces fit together into the function for a wave, which uses the cosine function. Regardless of these numbers though, all cosine waves basically look the same. The only difference is the details of how tall, wide, or fast the wave is. But things get very interesting when we add two waves together with different amplitudes, different frequencies, different wavelengths, and different phases. We can explore adding waves using VPython. Here we set the four properties for each wave. We'll start out by just looking at one wave, so we've set the second wave's amplitude to 0, meaning it will produce just a flat line. Next, we create each wave using VPython's curve object. A curve is a set of points connected by line segments. You can learn more about curves at the link in the description below. Then we set up each wave using the cosine function and the four properties that we set earlier. Finally, we come down to an animation loop where we move each wave forward as time increases. Let's run the code with a single wave set up. We see a recognizable cosine function that moves to the right at a steady speed. Changing the amplitude makes the peaks higher or lower. Changing the frequency makes the wave move by more quickly or more slowly. And changing the wavelength stretches or compresses the wave. Changing the phase doesn't make that big a difference with just a single wave, since the wave is repeating itself, but it will make a big difference when we add our second wave. Let's start by making the two waves identical. The result, as you might expect, is a much larger wave. We've basically taken the first wave and doubled it. We call this adding constructive interference. Things get to be more interesting when we shift the second wave's phase. Once the two waves are out of phase by 3.14, they're exactly out of sync and the total wave is a flat line. We call this cancellation destructive interference. Of course, 3.14 is the special number pi, which tells us that the phase difference is really an angle measured in radians. Things get even more interesting when we give the waves different wavelengths, and different periods. There is lots that you can play around with in this code to learn about waves. Follow the link in the description below to find a set of activities that will help guide you.